Hi, thanks for all coming. So obviously today I'm going to talk about counting low degree number fields by successive minima. Feel free to interrupt at any point, ask me any questions, or just any clarification. Yeah. Okay, so let me introduce the problem first. So in this talk, n will be an integer greater than or equal to 2. Our main object of study will be a non-degenerate rank n ring R. And by that, I mean a ring that's isomorphic to z to the n as a z module and has non-zero discriminant. So you should think of such a ring as being a product of orders in number fields, because that's exactly what this definition boils down to. Okay, so our main object of study is considering product of orders in number fields. So as number theorists, we obviously care about number fields. And when someone hands you an object that you care about, there's two immediate questions you can ask, which is what does it look like and how many are there? And today I want to combine those two questions together. So let me first talk about the first question, what does it look like? And the way I'll think about this question is as follows. R has n non-zero homomorphisms, sigma 1 through sigma n, from R to C. We can use these n non-zero homomorphisms to define a norm on this non-degenerate rank n ring as follows. So for every element x of R, we define the length of x to be the square root of 1 over n times the sum of the squares of the lengths of the embeddings. So if you don't like this norm, you can pick any norm you like, but I like this norm because the length of 1 is 1 and the shortest elements in the ring are roots of unity if the ring is irreducible. So I think it has some pleasant properties. Okay, so now that we've endowed R with this norm, it presents R as a lattice. And I will interpret the question, what does R look like, in the following way. How skew can R be as a lattice? In the space of lattices, where do the ones that we get from rank n rings sit? The second question I want to ask is a famous old question in arithmetic statistics. If you choose a permutation group, G and Sn, how many isomorphism classes of rank n rings are there where the discriminant is bounded and the Galois group is our prescribed group G? So today I'm going to talk a little bit about the first question.
So if it's a product of orders, what do you mean by the Galois group?
Oh, I just mean take the corresponding A-tail algebra, take the Galois closure of that A-tail algebra, and then take the Galois group of that. It might not be a transitive subgroup of Sn. Right, so I want to also consider non-transitive subgroups in this talk. So in today's talk, I'll first talk a little bit about the first problem, and then discuss how to combine these two problems together, and then talk about results. Okay. So the first problem I'm going to address using something called successive minima, which is a way to study how skew lattices are. And what are successive minima? Let me define them. So successive minima are n real numbers associated to a lattice, and we define them in the following way. For an integer I, from 0 to n minus 1, the ith successive minima of R with respect to our chosen norm is the smallest positive real number such that the ring contains at least I plus 1 linearly independent elements of length at most R. So you can see that successive minima are n numbers associated to the ring that tell us about what the ring looks like in a Euclidean sense. And of course, we want to understand the ring. So one of the first questions we can ask are what constraints can we put on the successive minima, given that it comes from a ring? So here are some constraints. Let delta denote the absolute value of the discriminant of R. The first constraint is that the successive minima are non-decreasing, and this is just directly from the definition. The second constraint is that the smallest successive minima is bounded below by 1 over square root n and is bounded above by 1. And if you fix n, you can basically just say, well, the smallest successive minima is a constant. It's not really telling us anything interesting, so we might as well abandon that data. Okay. Moreover, a famous theorem of Minkowski's says that the product of the successive minima is about the square root of the discriminant. This is roughly to say that the shortest elements, if you pick a short basis of your lattice, the angles between the vectors are bounded away from 0 in a way that only depends on n. Okay, so one question you can ask is this all the constraints? And the answer is no, but that's a story for another day. But if you're interested in that problem, I have a lot to say about it. So what I want to talk about today is the following problem. So we pick a point, P1 through Pn minus 1 in Rn minus 1. So we pick n minus 1 real numbers, and we pick a permutation group G, a subgroup of Sn. And I want to ask the following question. How many rank n rings are there such that the Galois group of R is our prescribed group G, the discriminant is bounded by some positive real number x, which you should think of as being very large, and the ith successive minima of R is approximately the discriminant to the pi for all I. So this approximately is something that needs to be quantified, and I will quantify it later in the talk. All right, does this question make sense to everyone? Cool. So let me write down a different way of thinking about this question for cubic rings that will motivate the definitions to come. If we have a cubic ring R, we have two numbers associated to it, lambda 1 of R and lambda 2 of R. And it turns out that it's pretty natural to take a log of both of these successive minima with respect to the discriminant. So combining these two numbers together, we have a tuple of two real numbers. So this is the element of R2. So for every cubic ring, we're getting a point of R2. So we get a bunch of points of R2 as we take the set of all cubic rings. And then we can take the closure in the Euclidean sense. We could take the set of limit points in the Euclidean sense of that set. And it turns out that we just get a line segment. And the question I want to ask is, for every point on that line segment, how many rings are there of lambda discriminant that lie close to that point? That's another way of phrasing this question. And that's the way I want to approach this question.
So it's contained in a line segment, or you already know that it is a line segment?
You have to prove it, but if you take the set of all points coming from cubic rings and then take the set of limit points of that set, you get a line segment. But yeah, you can prove that. But it's not immediately clear. Okay, so that's the way I want to approach this question, as thinking of each ring as giving you a point of Rn minus 1, and then you just ask how many rings are there close to each point of Rn minus 1. Okay, so this is not the first time this question has been asked. In fact, there's a lot of previous work on this question. So let me give you a non-comprehensive list of examples. So the first is Anand Patel's PhD thesis, worked on the geometric case of this problem over C, which has to do with Hurwitz spaces and scroll invariants. And he worked on this problem for n equals 3, 4, 5, and the Galois group Sn. And in fact, our results today will match the results of Anand Patel appropriately translated. Valchish-Lapierre, in his PhD thesis, worked on the number field version of this problem, the version I've stated here, also for low degree, n equals 3, 4, 5, transitive groups G, and the situation where the P1 through Pn minus 1 are very close to each other, i.e. the lattice isn't too skewed. So he studied when the lattice is not too far away from the cusp. No, sorry, not too deep in the cusp. Okay, and Wanlin Li worked on the function field case of this problem in her PhD thesis, in particular, when the degree is 3 and the Galois group is S3. So I won't talk about the geometric and function field versions of this problem, but they're pretty interesting. So yeah, again, ask me after if you're interested in those problems. Okay. So let me tell you, actually, let me make a note. So everything I'm going to say from now on in this talk is original work, including the setup, unless I specifically say that it's not. So in particular, these previous results were phrased in a pretty different setup. Okay, so let me tell you the setup for cubic rings. So let n3 of x denote the number of cubic rings of bounded discriminant. So we want to compare this number n3 of x to the number of cubic rings of bounded discriminant fixed Galois group that are near some point on this line segment. So we have two numbers and we want to compare them. So let me define the second number. So choose a point, P1, P2, and R2, and a permutation group G and S3. Then let me unpack this definition a little bit. So we define a number N3 P epsilon G of X, where here epsilon is a positive real number, X is also a positive real number, G is our permutation group in S3, and P is a point of R2. So we define this number to be the number of cubic rings R such that the Galois group is G, the discriminant is bounded by X, and the ring is close to P in the following sense. So if we take the ith successive minima, take the log of that with respect to the discriminant, and look at the Euclidean distance of that point for Pi, that Euclidean distance is bounded above by epsilon over log X. So this choice of epsilon over log X is a choice of a way to quantify this approximately. And you could ask, is this the natural choice? Is this the correct choice? And I think it is, because it translates from the geometric and function field setting really well, and it produces nice results. But one could, of course, make a different choice of what it means to be close to P. Okay.
What do you mean by that? You mean a sharper approximation?
Yeah, I mean, you could just,
You're proving an equidistribution, and that's the rate of it.
exactly, but you could put a different rate in there, right?
Well, if you can prove it.
I don't know, sometimes people are like, why is this the
Trying to
right?
understand what you mean by different. I mean, there's an equidistribution problem, and that the rate you're getting is at the scale, which I understand.
Yeah, I think, yeah, that's the correct way to put it. Okay, so now we have these two numbers and we want to compare them. And I define a density function in the following way. So an old theorem of Davenport-Heilbronn says that this term, N3 of X, is some constant times X approximately. And I expect this number to be approximately some constant times X to the power of alpha. And what I want to extract is that number alpha. So therefore, I define a function d epsilon of G from R2 to R union star, given by taking the limit of log N3P epsilon G of X over log N3 of X. So if you plug this in, you'll see that this top term is about alpha log X and this bottom term is about log X, so they'll cancel. And the reason the +1 is here is just to ensure that you're not taking a log of 0. And just because it's not a priori clear that this limit exists, I define d epsilon G of P to be star if that limit doesn't exist. In practice, the limit will always exist, but when we define this density function, we don't know that a priori. This is a product of the definition. Okay, so what we want to know is the value of this density function. And this has been computed in previous work, actually. So in the remainder of this talk, assume that epsilon is sufficiently large. Sufficiently large only depends on the ambient degree. Doesn't depend on anything else. So Val Shishlev here in his PhD thesis actually proved the density function for S3 qubits. And it has the following really nice formulation. So if our point P is in this line segment from 1/4, 1/4 to 1/6, 1/3, then the density function is this linear term over here, 1 minus P2 minus P1. And if it's not in that if P is not in that line segment, then the density function is 0. So it's quite nice. You can ask, what about other groups? What about maximal S3 rings? And in fact, we can compute all of these density functions as well. So this is my experimental way to demonstrate a theorem, or to state many theorems at the same time. So I'll explain what this means. If you take so you can define a density function for maximal S3 rings, where you just impose in here that you're just looking at maximal rings. So if you define a density function for maximal rings, you can compute it, and you see that it has the exact, so it's supported again on the slide segment from 1/4, 1/4 to 1/6, 1/3, and it has the exact same formula as the density function for S3 rings. So restricting to maximal S3 doesn't change anything. You can also ask about alternating group A3, and in this case, I actually don't know how to compute the density function, but I do know it's supported on this line segment over here. The same line segment, 1/6, 1/3 to 1/4, 1/4. If you look at C2, partially reducible cubic rings, then the density function is going to be supported on this line segment from 1/4, 1/4 to 0, 1/2, and it'll be given by this formula, 1 minus P1. And if you look at totally reducible cubic rings, which is what I mean by C1, the cyclic group on one element. Then the density function will be supported on this line segment, the whole line segment again, and we'll have a value 1/2 everywhere. And if you just don't impose any Galois condition and you just look at all cubic rings, then the density function is supported on this whole line segment, and it's given by this formula right here. So 1 minus P2 minus P1 plus the maximum of 0, comma 1/2 minus 3P1. And I just want to highlight a few things because the formulas will look really similar in other cases, in higher degree cases. So first of all, we have a 1 here, then we have minus a pairwise difference, and then we have plus a max. And you should think of every time one of these maxes is achieved, we've gone into some cusp. And I'll explain a little bit what that means more in the quartic case, but in the cubic case, this basically corresponds to the first coefficient of the binary cubic form being 0.
Is total the same as the maximum of the things above?
Yes. Yeah. Okay, so there's some other features we can see here. First of all, if you look at this total density function and you look at the values where that total density function equals 1, you get 2 points. You get this point over here, and you get this point over here. However, everything on here will be a reducible ring. So that implies that 100% of irreducible cubic rings of bounded discriminant lie close to here. So that same statement is a corollary of Bargava and Heron's work on equal distribution of lattice shapes of cubic rings, but here's another way to see that. Moreover, if you look at the density function for C2 and C1 and take their maximum, then you'll observe that 100% of reducible cubic rings of bounded discriminant lie near this point, which is also fairly easy to see using other methods, but this is a nice way to package all that data together. Moreover, if you look at monogenized cubic rings of bounded height, i.e. monic cubic forms of bounded height, then you'll see that 100% of those rings lie near here. And it's very important that I put bounded height here and not bounded discriminant because counting monogenic cubic rings of bounded discriminant is a very hard problem. And yeah, so we're just looking at bounded height. So this is another way in which we can see that monogenic cubic rings really act quite differently than general cubic rings, because general irreducible cubic rings all sit over here basically, and 100% of monogenized cubic rings of bounded height all sit over here. So it's one way to see the difference. And it's also sort of one way of explaining second order terms in cubic rings. And that's because if you plug in the density function for max or for S3 cubic rings here, you get 1. And if you plug in density function for S3 cubic rings here, you get x to the 5/6. And if you're trying to compute the total number of S3 cubic rings, you're essentially doing an integral over this line segment. And that means taking the indefinite integral at one point minus the indefinite integral at the other. So this is sort of a way of hinting that the second order term should be x to the 5/6 and the coefficient should be negative, which ends up being true. I'm not saying this is a way to prove that, but it's sort of a way of guessing that. Great, so I'm going to move on to quartic rings. Any questions about the cubic case?
That 5/6 can be seen from all of the Shintani zeta function,
Yeah,
for example.
I think there's a few different ways, right? But
I mean, that's what those things are good for picking up remainders. More so than remainders.
cool. I'll move on to the quartic case. I have a lot of pictures coming up in the quartic case, so I hope you like pictures. Oh, yeah, sorry, I want to make one more comment about the cubic case, which is that the answer that we're getting, this density function for S3 cubics, exactly matches up with the answer for the geometric analog of this problem when you, of course, translate that answer appropriately. So this is sort of the right setup and the right answer in that sense. Okay, so let me do the setup for quartic rings, which is going to be a little bit different than the setup for cubic rings.
To prove everything you stated, you're using Davenport's counting or?
Here?
Yeah, how do you prove these things?
Oh, yeah. So I just,
What's your method?
Yeah, I look at part of the fundamental domain deep in the cusp, and I thicken it by
But for binary cubics. Yeah,
binary
okay.
cubics, and I thicken it using unipones. And then once you thicken it using unipones, you get a box and you hang the box. It's essentially clever unfolding of the fundamental domain deep in the cusp. Okay, so let me discuss the setup for quartic rings. Okay, so instead of just considering a quartic ring, I want to consider a quartic ring along with a cubic resolvent ring. And for those of you who haven't seen cubic resolvent rings before, let me give you a quick way you can think about it. So if you take a quartic extension, K over Q with Galois group S4, then you can take the Galois closure, which I'm going to call K bar. This is some degree 12 extension of Q. And if you do some Galway theory, you'll see that inside K bar exists a cubic field I'm going to call C. So classically, this cubic field C is called the cubic resolvent field of K. And Bhargava developed an integral notion of this. So in particular, every quartic ring has at least one cubic resolvent ring, and every maximal quartic ring has a unique cubic resolvent ring. In the case that your order is the maximal order of a S4 quartic field with square-free discriminant, then the unique cubic resolvent ring is the maximal order in this field, C. So that's what you should think of if you haven't seen this before, but yeah, I'll just call them cubic resolvent rings. So consider isomorphism classes of pairs, R comma C, where R is a quartic ring and C is a cubic resolvent ring of R. And let G be a subgroup of S4, because now we're looking at the quartic case. Okay, so again, we define our density functions in the usual way. So N4 of X is going to be the number of pairs R comma C, such that the discriminant is bounded by X. We define N4 P epsilon G of X in the following way. So again, P is a point of R5, epsilon is a positive real number, G is a subgroup of S4, and X is also a positive real number. So this is going to be the number of pairs R comma C, such that the Galois group of R is G, the discriminant is bounded, and the successive minima of the quartic ring R are close to P1, P2, P3, and the successive minima of the cubic ring C are close to Q1, Q2. So I'm prescribing the successive minima of the quartic ring and the cubic resolvent. So that's what I'm counting. And again, a theorem of Bhargava's shows that this is approximated by some constant times X. And I expect this to also be some constant times X to the alpha. So again, I want to extract that number alpha. So I define the density function in the exact same way. So here, the density function is now a function on R5, taking values in R union star, and it's defined in the exact same way to extract that number alpha. So now I want to know the value of the density function. And you can compute it. So here's a theorem. So let me make one note. So here I wrote d epsilon G, and here I'm just writing d epsilon 4. And by d epsilon 4, I just mean the maxes as we range across all the groups. So this is just the total density function to take the max of all the d epsilon G's. Okay, so if P is in this region over here, then the density function is given by this formula. And if it's not, then the density function is given by 0. So you should immediately object, because you should say, hey, doesn't this density function take values in R5? Why did you just show me something in R3 and tell me that P is lying in this state? Well, the reason is because the support of this density function lies in the subset of R5, such that P1 plus P2 plus P3 equals 1/2, and Q1 plus Q2 equals 1/2. This is just a side effect of Minkowski's theorem, that the product of the successive minima is about the discriminant, and a fact that the discriminant of the cubic resolvent is equal to the discriminant of the quartic ring. So what I've done is I've computed the support of the density function in R5 and projected it to P1, P2, and Q1. So this projection will be a bijection onto its image, so you're not really losing anything. Right, so this is a depiction of the support. And you see that this density function has a very similar formulation to that of the cubic case. In particular, you have one, and then you have a bunch of pairwise differences. So these are the pairwise differences of the quartic. This is the pairwise differences of the cubic. And then you have a bunch of maxes that correspond to getting further and further into the cusp every time one of these maxes is achieved. I want to take a look at this density, the support of this density function. It's not convex, but it's a union of two convex bodies. It's a union of two polytopes. And let's take a little bit of a closer look at it. So here I've annotated some features of the density function, of the support of the density function. In particular, I've colored it in such a way that green is the points of highest density and this blue is the points of lowest density. So you can see that if you move along this line segment, the density is dropping. And if you look at the support, you'll see that there's 4 points on which the density function is 1. And those 4 points have sort of a different algebraic meaning. So I've marked some Galois groups here. In particular, 100% of S4 quartic rings of bounded discriminant lie near here. So this is sort of the generic point for S4. This is where the S4 things lie. 100% of D4 quartic rings of bounded discriminant lie near this vertex over here. And 100% of S3 cubic rings of bounded discriminant lie here. And 100% of S2 cubic rings of bounded discriminant lie here. So there's really like different algebraic interpretations as you move along this polytope. Just to say a little bit more, this region of the polytope, of the support, in this region of the support, every ring is going to be, every quartic ring is going to be reducible. And then in this region of the support, every cubic resolvent ring is going to be reducible. And that sort of forces the S4 things to lie here because the quartic ring is not reducible and the cubic resolvent ring is also not reducible. And in fact, you can see it. So here's the density function for S4. It's exactly the same as the density function for general, but the support is smaller. So it's just a restriction. So the density function for S4 has the exact same form if P is in this polytope below, and if P is not in that polytope, then it's 0. So let me try to show you how this polytope sits inside the general one. So just sort of remember how this looks. And it goes right here, essentially. That's where that sits. And I'll show you them side by side later.
Some of the differences, it reflects some kind of harm measure on the, it looks like the, harm measure of the TL3 times TL2 or something like that. Is that how it arises? Or
I see it arising as degenerations of a Minkowski basis. Like if you have a cubic ring lying near 1/6, 1/3, then the number of short bases of it is about x to the 1/6, because you can add copies of the smaller vector to the larger vector. It's probably the same thing, I think. It's just like sort of the number of short bases of that ring. So this is like the adjustment factor for the number of short bases of the quartic ring, and this is the adjustment for the number of short bases of the cubic ring. Is that the same thing? I think it. Yeah. Okay, so as you can see from the density function, it is continuous and piecewise linear. And here's a drawing of the 3 components on the support, where the density function is linear on each component. And I've drawn out a few more things so you can see sort of features of this density function. So the first is, as I said, this is the generic point for S4. So 100% of S4 things lie here. This is the monogenic point. So if you look at monogenic quartic rings of bounded height, then all of them lie here. And the reason for that is sort of as follows. So if you take a monogenic quartic ring, R, and the monogenizer is Z adjoint alpha, then because it's a monogenic quartic ring, we know that it has this basis as a Z module. 1 alpha squared, alpha cubed. And generically, we would expect this to be a Minkowski basis. So we expect the size of the first successive minima to be about the size of alpha, the size of the second successive minima to be about the size of alpha squared, and the size of the third successive minima to be about the size of alpha cubed. And that's why the monogenic point is different from the generic point. Moreover, if you have a monogenic quartic ring, the cubic resolvent ring is also monogenic. So this is, so let me tell you the axes. This is the P1 axis, this is the P2 axis, and this is the Q1 axis. So monogenics are more skew in both the quartic ring and the cubic ring. And that's why we've gone back in P1, P2, and Q1, because everything is more skewed. Both rings are more skewed. Okay. 100% of binary quartic forms of bounded height lie near this vertex right here. So let me explain what that means. If you take a binary quartic form, there's a natural way of constructing a quartic ring from it and a cubic resolvent ring as well. And if you take a general binary quartic form, then the quartic ring coming from it is not going to be especially skewed. It's probably going to be roughly the same size. And that's why if you look at the generic point and the binary quartic point, we haven't changed in the P1 axis or the P2 axis. We've only changed in the Q1 axis. And that's because if you take a cubic resolvent ring of a quartic ring arising from a binary quartic form, that cubic resolvent ring will be monogenic. So therefore, on average, will be more skewed. So that's why binary quartics lie over here. And these three other vertices that I've left unmarked also have sort of algebraic interpretations in terms of having sort of different basis structures, but I haven't written them here. And for those of you who are interested in arithmetic statistics, probably a large proportion of this audience actually, you often hear the word cusp. And in particular, if you look at the parametrization of binary quartics, quartic rings. Quartic rings are parameterized by tuples of Riemann symmetric matrices, A comma B. And the first cusp is when B11 is 0, and deeper in the cusp is when B11 equals B12 equals 0. And all the rings in the B11 equals 0 part of the cusp lie here, and in the B11 equals B12 part of the cusp lie here. So we see that the density function changes. It has these transition points when we enter a deeper in the cusp, essentially. So I think this is neat. I think it packages a lot of features together. And again, this S4 answer matches up with the answer for the geometric analog of this problem. And just to say a little bit about the geometric analog of this problem, what we're doing there is we're taking the Hurwitz space of degree D covers of P1 of genus G. We fix a set of Scroller invariants, and we look at the locus in the Hurwitz space of fixed Scroller invariants. And then we normalize, and then we take the dimension of that locus, and then we let G go to infinity. And that's the analog, and you get the same functions. Okay, I'm going to talk a little bit about D4 now, but any questions on this S4 setup?
Can you also say the secondary terms, they have something to do with this geometry, this polytope?
No, I don't know enough to say something about it, but definitely all the action lies on this boundary and this boundary. So I'm not sure.
That would be very interesting.
Yeah, I haven't been able to say anything about it, but it's about all these boundary components of this polytope, I think. But yeah, that would be something really interesting if you could predict the second order terms using this model. But you have to understand the boundary better and sort of how things transition to that boundary. Yeah. So let me talk a little bit about D4. So if you take the D4 density function, then its support will be a polytope, which I call poly D4. I'm just going to call this polytope right here, this thing, poly S4, the support of the S4 density function. So then if you take a point in the D4 polytope that's not in the interior of the S4 polytope, then this is the value of the D4 density function. And if P is not in the D4 polytope, then the density function is 0. Okay, so let me give you a picture of the D4 density, of the D4 polytope. So this is the polytope right here. It strictly contains the S4 polytope. See if you can see how it sits inside. So if you go here and you take a look at this polytope, you see that that front face of the S4 polytope is this face right here, the D4 polytope.
So how can I think about this? Can I think about that? How do I think about that formula?
Yeah, so I would think of the formula as saying,
That is, suppose I wanted to guess it, not necessarily to prove it.
yeah. So if you write it down in the parameterization for quartic rings, if you take some D4 thing and you write it down, you get 2 matrices. And suppose you put everything in Minkowski basis and then you fill in these matrices. For a generic D4 ring, I would expect all these things to be 0.
But that's somewhat specific to your parameterization. So you explained earlier, I could see the sum of differences as counting short bases.
Yeah.
Is there a way in that spirit you could see the correction that comes after it?
Oh, the maxes?
Yeah, this Q2 minus 2P1 and so on.
Hmm.
Because I previously you said it was very nice because it applies situation.
I'm not sure, but I guess I think of it as counting like the number of options to put in these matrices when you put everything on Minkowski basis. But in D4, I'm guessing that at every point generically, you can make these things 0. So the options to control these 3 elements sort of go away. That's where the correction is. I guess another way to say it is at any point in this polytope, if you look at all the D4 things close to it, I expect 100% of those to have shortest vector in a quadratic subfield. Yeah, I'm not sure if that answers the question, but yeah. So the reason I wrote it this way is because this is what I expect the D4 polytope to be even inside the S4 polytope. And one evidence towards that conjecture is that it's a lower bound. If you take the lim if, then you actually can bound it by this. And that sort of comes from doing the count where you just fix certain elements of the parameterization to be 0. Okay, so here's another picture of the D4 polytope, colorized again with the density function. So green is the highest value of the density function and purple is the lowest. So you see it transitioning along this polytope. And you see that the generic D4 point is here, meaning that this sort of says that a generic D4 ring has a quadratic subfield with very small discriminant, which is why the first successive minima is very small because it belongs in that field in that quadratic subfield with very tiny discriminant. Great. So this is, I just wanted to put these next to each other so you could compare them. This is the support for the total density function. This is the S4 density function, and this is the D4 density function. So this D4 thing is essentially this component right here, if you can imagine. And this S4 polytope fits right here with like this thing lying in here. Actually, I have a little printed model if anyone wants to play with the S4 polytope. A little like 3D printed model, but I can show that after, or if someone wants it. Anyway. So yeah, so any more questions on quartics before I talk about quintics?
Sorry, which one is the S4 polytope?
Oh, the middle one is the S4. And this is D4. So you should think of this as shrinking all the way down, and then this face is going here. And then this D4 goes here. I should have put little colors to mark the vertices so you know how to line them up, but yeah. So let me talk about quintic rings. In the quintic case, we want to consider pairs R comma S, where R is a quintic ring and S is a sextic resolvent ring of S. So for people who haven't seen this before, let me also explain briefly what a sextic resolvent ring is. And it's the following. So if you take, it's almost exactly the same as the quartic case. So if you take a field K, a quintic extension of Q, and suppose it has Galois group S5. Then again, you take the closure and you get some extension. And inside this extension sits a degree 6 field that's classically called the sextic resolvent field of K. So again, Bhargava developed an integral model of this. So to each quintic ring, there exists at least one sextic resolvent ring. And we're going to consider isomorphism classes of pairs, RS, where R is a quintic ring and S is a sextic resolvent ring. One important thing to keep in mind is that in the quartic case, the discriminant of the cubic resolvent equals the discriminant of the quartic ring. But in this case, that's not true. So here, the discriminant of the sextic resolvent will be the cube of the discriminant of the quintic ring. So it's just important to keep that in mind. And now, because we're in the quintic case, G is going to be a subgroup of S5. Okay, so I just want to refer to these supports of these density functions explicitly. So I'm just going to make a definition so I can refer to them. And the definition is the following. So if we fix a group G and we look at all pairs, and we have a pair R comma S, such that the Galois group of R is G, then we can use that pair to get 9 positive real numbers in the following way. So we take the 4 successive minima of the quintic ring, and take the 5 successive minima of the sextic ring, package them all together, and then take a log with respect to the discriminant. So we get 9 real numbers, we get a point of R9. As we range across all pairs, we get a bunch of points in R9, so we can take the limit points of this multiset, and I'm just going to denote that by poly G. So that way I can explicitly refer to the support of these density functions. Okay, so this is basically just the polytopes we had earlier. And now I define the density functions in the exact same way. So n5 of x will be the number of pairs R comma x, such that the discriminant is bounded by x. For a point P1 through P4, Q1 through Q5 in R9, so now P1 through P4 will refer to the successive minima of the quartic, Q1 through Q5 will refer to the successive minima of the quintic. We define N5 P epsilon G of x to be the number of pairs R comma x, such that the Galois group is our fixed group G. The discriminant's bounded by x. The successive minima of the quintic ring are close to the P1 through P4, and the successive minima of the sextic ring are close to the Q1 through Q5. So exact same definition. Again, by theorem of Bhargava's, n5 of x is about a constant times x, and we expect this top thing, n5p epsilon g of x, to be about a constant times x to the alpha. We extract the alpha using this density function, and we want to understand the value of this density function. Okay, so it has a super nice form, exactly the same as before. So if P is in the union of poly G, as we range across all subgroups of S5, then the density function has the following form. So again, it's 1 minus a bunch of pairwise differences coming from the number of Minkowski bases of those rings, plus some correction terms for being in the cusp. So this is the correction terms for being in the cusp. And if P is not in the support, then of course P is 0. Yeah, so I'll just leave this up for 10 seconds if anyone wants to stare at it. I think this formula is super nice.
I wonder if these formulae have any relation to Arthur's truncation. Have you ever?
I've never heard of it, but
He's got a truncation in the cusp, which has got a similar flavor of, you know, I think it's related to what Akshay said, where you're looking at different subgroups and stabilizers. And these are linear functions of that. And he's got an exponent. In fact, it's a truncation, and when you, whatever you declare the trace formula to be, it's the value of this function at the origin as a function of t. And since this whole game you're playing is about not the cusp in the standard fundamental domain, but on this in this action, sounds like it's got to be related.
oh, maybe.
Looks, you don't go more than 5 to prove anything, probably.
Yeah. But you can make guesses, right?
Yeah, I'm sure you can.
Maybe the guesses won't be right, but you can make guesses.
Nobody will prove you or disprove.
Yeah, exactly.
You do what you like.
Yeah, exactly. Okay, so we have this general density function, and just as you expect, the S5 density function is just a restriction of this, the same density function, like literally the same formula, to just a smaller region. And we can compute poly S5, and I want to show you a picture of it, but unfortunately I can't because it's a 7-dimensional polytope in R9. But what I can do is the following. I can take poly S5 in R9, project it down to P1 through P4. This is a lossy projection. Project it down to P1 through P4. Notice that the sum of P1 through P4 is 1/2. So then project it down to P1, P2, and P3, because you can deduce P4 from P1, P2, and P3.
Let me go back to a related question that
Oh, okay.
actually asked. So if you take the Shintani zeta function, which have been computed for all these things, they smooth usually, if I remember. And then they have poles in various places. Those poles must have a meaning for you in your picture. They must be very clear in all cases what those poles are, because these have been computed for these, or what they call pre-homogeneous vector spaces. I think they've computed those poles. And you clearly explained it in the cubic case, because you had that 5-6, I remember that one.
Yeah, it's not entirely clear to
I
me.
mean, that's got less information than yours, I think. So in other words, when you draw your picture, you'll probably also be able to say, here are where the poles of this Shintani zeta function.
I think the poles will probably line up with key boundary points, right? Like vertices or internal boundary points or something. But I haven't mapped them out. But
Yeah, it's really worth doing because like I think not all the poles show up as secondary terms.
Right, sometimes, and there's some issues there that people, I mean, we had a lecture about fauna or something, remember?
yeah,
Lemke or something.
yeah. Yeah, I think, well, it's pretty easy to get candidates, right? Because you can just look at the vertices, compute the density function of all the vertices and see how they line up with the poles and see which ones are the same. And then you can be like, okay, this probably lines up with this, but it's only on that surface level I've done it, not anything more, but I think I should. But yeah, so the S5 polytope, so I computed the S5 polytope and projected it down to P1 through P4, P1 to P3, and then here's a picture of the S5 polytope. I haven't marked it, but you can imagine all the same things, different vertices.
Yeah, I forget what's a pre-homogeneous vector space for 5.
It's 4 tuples of 5x5 alternating matrices, fraction of SL4, SL5 gem. Yeah, so this is the polytope. So for the last 10 minutes of the talk, I want to move on to a slightly different question, which is asking about successive minima of sextic resolvent rings of quintic S5 rings.
Sorry, can you is it easy to describe that support? Is it for the S5 thing?
Yeah, it has a bunch of, yeah, so it is, here's the support, I can tell you. So the sum of the PIs is 1/2, the sum of the QIs is 1/2. The PIs are non-decreasing, the QIs are non-decreasing, and then there's 7 other linear inequalities that all kind of look like this is greater than 0 or something like that.
Involving 3 PIs, for example.
Involving
Or PIs and
2 Qs and 1 P and a half.
And do you think that would be valid for larger values of n?
I think that you could define a region that would contain the support, but I think the support would be smaller.
Oh, it would have some additional inequalities that you haven't seen.
Yeah, and I think this thing I want to talk about will sort of suggest why that's true.
Okay.
Right, so if you have a quintic ring R with Galois group S5, and you take the sextic resolvent ring of that quintic ring, then a little bit of Galois theory will show you that the Galois group of S is S5, where here S5 is transitively embedded in S6. Okay. However, not every sextic ring with Galois group S5 transitively embedded is a sextic resolvent ring. So you have a bunch of S5 sextic rings that are sextic resolvent rings, and then you have a bunch of S5 sextic rings that are not necessarily resolvent rings. I want to ask, like, are the successive minima of these things different? And Yeah, so I want to compare the successive minima of sextic resolvent rings of S5 quintic rings to the successive minima of irreducible S5 sextic rings. And to my great surprise, it turns out they're not the same. We really get different regions. And here's a way to sort of formalize that. So take an irreducible S5 sextic ring S, take its 5 successive minima, take a log with respect to the discriminant of the sextic ring, and you get a point in R5, and then range over all such sextic rings, and you get, and take the limit points of that multiset, and denote this region by P. On the other hand, let pi from R9 to R5 be the projection onto the last 5 coordinates. So what is this doing? This is saying, so the projection of poly S5 the projection of poly S5 is going to be the same as taking the set of all sextic rings that show up as resolvent rings of S5 quintics, plotting them in R5, plotting their successive minima on R5, and then taking the set of limit points. So I want to compare the set P to the projection of poly S5. And one thing you can prove is that 3P strictly contains the projection of poly S5. And okay, one thing you should ask is why did I multiply by 3 here? Yeah, the 3 is just because in
the discriminant.
the discriminant's a cube. So it's just adjusting for the discriminant, because here we're taking a logarithm of something that's the base is the cube of the other base. So the 3 is basically not important, but yeah. But anyway, 3P strictly contains the projection of poly S5, which means that resolvent rings really have additional constraints on their successive minima. And the way the explanation I sort of see for that is the set of resolvent rings in the set of S5 quintic rings is something like a subvariety or some sparse subset. And therefore, there's additional constraints on their successive minima. And that's why I'm guessing, to answer your question earlier, that you'd actually get a smaller subset, and that wouldn't be all of them. Okay, that's actually all I was planning on saying today. But if anyone has any questions, please ask, and thank you very much.
So in the function field case, what would you be looking at?
Yeah, so in the function field case, you would be counting the number of covers, fixed degree, fixed genus covers of P1 with prescribed scroller invariance. And then letting the genus go to infinity and normalizing appropriately. Does that answer the question? Or?
I think I asked Haran or maybe Manjul at her thesis defense, what happens if you look at the joint distribution of this lattice of the ring and of the units?
Oh, of the units.
Together in a joint space.
Oh.
You know, anything? I think that, of course, the units are deadly, but when you order by discriminant, which you do, but
that's a
you should think about it.
Yeah, I haven't thought about that. That's a good question. I have wondered if the regulator changes along these polytopes.
Don't worry about it too much. It's painful. But it is a good question. The answer is very difficult, probably. But I mean, whenever trouble is we don't know the distribution of the second thing, really.
Yeah.
Although maybe, anyway, it's a question. Then you could do the successive minima across everything.
Yeah. Yeah, that's a good question.
And you could also do equidistribution. You could look at this not over the Archimedean place. Can't you do something p-adic as well? Take some completions and ask about. I'm sure you've asked that, right?
I don't know the right way to phrase the question.
Maybe not the successive minima, but if you look at lattices, whenever you have a space of lattices, you can ask millions of questions about equidistribution, and that's what you're asking. So, did Lindenstrauss do something else after them? Actually, I forget now on this question of this distribution of the lattices in, maybe he wasn't ordering, thought he did something. After Manjul and Paris.
Wait, what?
Aaron. What's her name?
Oh, what did he do?
I think he did ask some question of that nature.
Oh,
And maybe answered it. And successive minima is one thing you look at with lattices, but you can look at millions of other things.
yeah,
They're all natural questions. What you're doing is you're refining Manjul's count.
yeah,
He's counting the number of number fields. You're now counting the rules decoration, which we love. Yeah.
yeah.
Maybe you said, I didn't hear, but do you have anything for like maximal S5 things
Oh.
or?
Yeah, so actually the tail estimate is really easy. So the only thing left to do is check that the product of local densities is non-zero, which I would be shocked if it was non-zero, and I computed them, but I just have to do some work and
You'd
check
be
it.
shocked if it is non-zero?
I'd be shocked if it was zero.
Oh, okay.
So yeah, I would expect it, and I don't think it's that hard. I just haven't finished doing the calculations.
This was what? The lower bound?
Maximal S5.
But you had some theorem there. I was a bit surprised you only had a lower bound.
Oh, the D4?
Why was that?
Oh, because in the S4 polytope, let me pull up a picture. Yeah, so in the S4 polytope, 100%, if you pick a point on the interior of the S4 polytope, 100% of the rings are going to be S4. So if you want to count D4 rings, it's sort of hard because they're kind of sparse. So I have a hard time getting an upper bound for that reason. I mean, I just don't know how to, but maybe there's a way. With the lower bound, you can just construct a bunch of D4 things and be like, okay, they're here.
The D4 is usually class field theory. You can count those more easily. My memory was that when Manjul was doing S4 was hard, D4 was there was a lot of progress. Maybe they'd already done it.
But if you want to count it with classical theory, you sort of have to know that the shortest vector lies in a quadratic subfield, right? You have to know how long the shortest vector is.
Yeah, it's true. You're putting on this constraint. Yeah.
And I don't know, like if you pick some point in the S4 polytope and you look at all the D4 things near it, I don't know that 100% of those have shortest vector in a quadratic subfield. I think that's the only thing I would need to know.
Yeah. Okay.
So do you have conjectures for higher end?
Oh, I thought, let's see. I thought for a while that, let me pull up the S5, that you can basically just generalize this based on the shape of the resolution, and that would be the correct thing. But this last thing I said about the resolvents having different structure, I didn't expect that at all. So now I'm reconsidering whether I actually expect this generalization of this formula to be true.
You mean the resolution of the ring or something?
Yeah.
Yeah. Oh, yeah.
So, I mean, I have some guesses, but I would guess my guesses are wrong.
Okay.
I don't know how to make better guesses.
Okay, cool.
Cool. Yeah, thank you for all the questions.